This is the second part of feedback amplifiers, in which the previous one I have explained the different topologies and I have derived the equation for the input impedance with feedback in case of voltage series feedback, voltage shunt feedback, current series feedback, and current shunt feedback. In this presentation, I will be looking into the how it does it affect the output impedance of the amplifier. So let us see how can you calculate the output impedance in the feedback circuit. Different types of feedback circuit like voltage series, current series, and voltage shunt and current shunt feedback circuit. The general principle in calculating the output impedance is like this one. That is, to calculate the output impedance Z0F is, first one is that the input voltage source is short circuited, and if the input is a current source is open circuited. If the input is a voltage source, that is short circuited. If the input is a current source, it is open circuited. Means that replaced by its internal resistance, if there is. Normally, if you neglect the internal resistance, it will be neglected, and the voltage source will be short circuited and current source will be open circuited. Next step is that then we are connecting a voltage source at the output side, V0 at the output side. Now let the current drawn by that circuit is equal to, say, I0. Then we can calculate the output impedance as Z0 as V0 divided by I0. That is the output impedance. This is the way in which how the output impedance of a circuit can be calculated. This is a generalized principle. Now let us see for different topologies how the output impedance can be calculated. Let us calculate the output impedance of a voltage series feedback circuit. For a voltage series feedback circuit is a block diagram in which this is the amplifier and this is the feedback circuit. Since this is a voltage series feedback, we are sampling is the voltage, and series means the feeding back signal is added in series, or here voltage is this one that is added, not added, it's subtract actually. This voltage is subtracted from the input and you'll be getting the VI equal to Vs minus Vf. Therefore that is in series to this one with a negative minus here and plus here. Therefore this is a voltage series circuit block diagram in which gain is equal to, it is the output is a voltage and input is also voltage. This is a voltage gain. V0 divided by Vi. Normally that is represented by AV. It's a voltage gain. And feedback factor is equal to output is a voltage and input is also, this series also voltage. Therefore it is output Vf divided by V0 equal to beta, or Vf is equal to beta times V0. Therefore this is a voltage series feedback circuit. Now let us see how the output impedance can be calculated. As we have already seen that one thing is that you have to remove the input voltage source and short circuit by that one. If it is a current source, it is open circuit. Because this is a voltage source, we have to short circuit at the input side. We are shorting at the input side. Now we are applying a voltage V0 at the output side. At the output side, we are removing the load and we are connecting a voltage V0 at this one. And if it is taking a current of I0, this ratio we call it as output impedance. V0 divided by I0 is called the, what is the impedance looking from this side? That is called the output impedance that we have to derive. Now coming to the this output loop here, applying the Kirchhoff's voltage law to the output loop of this one, we will be getting, it is equal to the output voltage V0 equal to I0 Z0 plus AV into Vi, AV into Vi. Therefore we are writing the loop equation for this one, V0 equal to I0 Z0 plus AV into Vi. Next we are going to write the voltage KVL equation to this input loop. Input loop, if you write it, it is equal to this is the voltage plus minus here, Vi plus Vf. Vi plus Vf is equal to 0 because we are shorting this one, or Vi is equal to the input voltage to the amplifier is equal to minus times Vf. Now substituting this Vi in this equation for as Vf, we will be getting, it is V0 equal to, which is I0 into Z0 minus AV into Vf. Now coming to the Vf, Vf is what? Vf is equal, this voltage Vf is given by beta times V0. Substituting that one for Vf here, beta times V0, in that one we will be getting the output voltage V0 equal to I0 Z0 minus AV into beta times V0, or grouping the V0 terms here, V0 into 1 plus AV into beta equal to I0 divided into Z0, or we can say that V0 by Z0, that is called Z0F, that is output impedance with feedback. Z0F is given by V0 divided by I0, that is equal to Z0 divided by 1 plus AV into beta. Therefore, impedance with feedback in a voltage series feedback circuit, impedance with feedback Z0F equal to impedance without feedback Z0 divided by 1 plus AV is the voltage gain of this amplifier, and beta is the beta factor, feedback factor beta. For Z0 divided by 1 plus AV into beta, meaning that output impedance is getting reduced if the sampling is the voltage. If you are sampling the voltage, output impedance is reduced. Therefore, in a voltage sampling feedback circuit, the output impedance is reducing as per this equation Z0 equal to Z0 divided by 1 plus AV into beta. Doing the derivation of output impedance in the second topology, let's say voltage shunt feedback, in which the sampling is same as the previous one. You are sampling the voltage, but mixing is shunt here. We are injecting the current that is subtracted from this one, that is resulting the input current. So the sampling is voltage, but mixing is shunt or current mixing. And now let us see again this one. This is an amplifier in which output is a voltage and input is the current. Output voltage divided by the current. Therefore, this is the RM is the trans resistance is the amplifier. Trans resistance amplifier in which output is the voltage and input is the current. And the feedback factor out. This feedback input is the voltage and output is the current. Therefore, current divided by IF divided, here the output is the current. IF divided by V0 equal to beta, or the feedback current is equal to beta times V0. Therefore, this is a feedback circuit in which voltage is sampled and current mixing or shunt mixing. Now coming to the to find out the output impedance, as we have seen, if the input is a current source, we have to open circuit. Therefore, we are open circuiting at the input side and we are applying a voltage source at the output side V0, and you are watching what is the I0. V0 by I0 is the output impedance with feedback. Now coming to the, you write the Kirchhoff's voltage law to this output loop. V0 equal to the drop across R0, I0 into I0 into Z0, I0 Z0 plus this one. This is a voltage. Actually, this voltage is given by RM into II. RM into II. Therefore, RM into II. That is the equation for the Kirchhoff's voltage law to this output loop. Second is that if you write the Kirchhoff's current law to the input side, here Kirchhoff's current law here, and because it's open circuited, applying the KCL at the input side, we can write it as II plus IF. The input current plus the feedback current, that is equal to 0, or the input current is given by minus times IF, minus times IF. If we are replacing this II by this minus times IF, we will be getting the output voltage equal to I0 Z0 minus RM into IF. Now IF is, what is the feedback current? IF is given by, it is equal to beta times V0. We are substituting that one, IF equal to beta times V0, and substituting for this IF here, V0 equal to I0 into Z0 minus RM into beta times V0. Now again grouping the terms of V0, V0 into 1 plus RM into beta, where RM is this trans resistance gain or RM, and RM into beta equal to, we will be getting, it is equal to I0 into Z0. Or this ratio, that is called the output admittance, output impedance, sorry, not admittance, impedance. Output impedance is given by V0 divided by I0. Therefore, V0 by I0, which is equal to Z0F. Output impedance with feedback is equal to V0 by I0 is equal to Z0 divided by 1 plus A beta into RM. A beta into RM, where RM is the transconductance, which is equal to the output voltage divided by the input current, trans resistance. This is called the trans resistance RM. Therefore, in this case also, the output impedance equal to, with feedback equal to output impedance without feedback divided by 1 plus A beta into RM. And because of the numerator term, this one, the gain is, the impedance is getting reduced. Therefore, the output impedance is reduced in a voltage sampling feedback circuit, the output impedance is reducing. Therefore, generally we can say that if you are sampling the voltage, the output impedance is reducing. That is reducing by like this one, Z0 divided by 1 plus A beta into Rf. Now we are going to derive the output impedance equation for a current series feedback. Now in this case, output side, the sampling is the current. We are taking the current information from the output, and that is added, that is out, that is mixing is also, mixing is the voltage. We are sampling the voltage. That is why the output is the current, and to this one, output is current and the input is the voltage. Current divided by voltage. This is called transconductance. Therefore, this is called GM. This is called a transconductance GM. This amplifier is called a transconductance amplifier, in which that converts the input voltage into the output current. Therefore, output current, certain portion of the output current is fed back as the voltage. That ratio we call it as feedback factor, which is equal to the beta is given by the feedback voltage divided by the output current, Vf divided by I0, or the Vf is equal to the feedback voltage which is subtracted from the input voltage, that is equal to the beta times the output current, and the resulting voltage at the input side, that is multiplied by this Gm, will be getting the output current. So this is the circuit diagram of a, or the block diagram of a, say block diagram of a current series feedback circuit. And to calculate the output impedance, as we have already seen that one thing is that you have to remove this, since the input is a voltage source, we are removing, it's open, sorry, it's short circuited. Therefore, we are out on the input side, you are short circuiting, and the feedback signal is applied, Vf is applied, and at this side and the input side, actually this is a, if you replace this one as a output is a current, that is why we are applying it as a Norton's equivalent circuit, like this, say is a current source with a magnitude of Gm into the input voltage Vi. That is the magnitude of this current here, that is current coming, and this is the output impedance Z0, and this is the equivalent circuit looking from the outside of the output of the transistor, and that is given to a voltage source is applying here, and the current taken is, in this case the current taken is represented as I, but because this current is I0, that is why, just to differentiate that one, this current is taken as capital I, and this voltage is taken as the output voltage V0. Therefore, we have to find out the ratio V0 divided by I, that is the output impedance with feedback. Now, to find out that one, first you are going to apply the Kirchhoff's voltage law to the input loop and output. Let us see first the Kirchhoff. First, we have to apply the Kirchhoff's current law to this output loop and Kirchhoff's voltage law to the input loop. Applying the Kirchhoff's current law to the output loop, the current flowing through this one is given by V0 divided by Z0. Similarly, that is the current in this direction. In this case, current direction is opposite. That is why it is marked as, it is equal to, that current is marked as I0, this mark, which is equal to Gm into Vi. Therefore, that is I0, this current is marked as minus I0. Therefore, minus I0 plus V0 divided by Z0, that is the current, that is this one, that is this current is equal to I, capital I is that. That's the equation applying the Kirchhoff's, deriving after applying the Kirchhoff's current law to this output loop, or sorry, output node. At this point, we are applying the Kirchhoff's current law. Now, applying the Kirchhoff's voltage law to at the input loop here, we can get it as, this is shorter, this one, Vi plus Vf equals 0, or Vi plus Vf equals 0, or Vi equal to minus Vf. Input voltage Vi equal to minus times Vf. And Vf is nothing but, the feedback voltage is nothing but beta times I0. Beta times the I0 is the, here, beta times I0 is the feedback voltage. Now, substituting like here, Vf in this equation here, substituting here the this one here, Vf equal to beta times I0, substituting equation 3 and 2 in equation 1, you will be getting I equal to, that is the current I, this current I equal to V0 by, of course, V0 by, actually this is equal to Z0, V0 by Z0 minus Gm into beta times I. Grouping the terms in I into 1 plus Gm into beta equal to V0 by Z, or Z0F is given by whatever this voltage, that is the voltage here, that is V0, that is divided by this current I, that is V0 divided by this current I is given by Z into 1 plus GM into beta. Therefore, output impedance with feedback equal to output impedance without feedback into 1 plus GM into beta, where GM is the transconductance gain GM and beta is the feedback factor beta. Therefore, here output impedance, if you are looking from this one, output impedance is more than with feedback is more than without feedback, meaning that if the sampling is the current, the output impedance is increasing. In current sampling feedback circuit, the output impedance increases. That is the general statement. That is, if you are sampling the current, the output impedance is increasing from Z0, actually Z0 to 1 plus Z into 1 plus GM into beta. That is Z0 F is equal to Z into 1 plus GM into beta. One more feedback topology is there, in which it is a current shunt feedback. Current shunt feedback itself, the sampling is the current and the mixing is the shunt. That's the meaning. This is the type of the sampling and this is the type of mixing. Therefore, we are sampling from the output, current is taken, and we are mixing, shunt is the mixing. Therefore, again current is mixing. Therefore, it is input side also, it is a current is mixing and output is also current. That is why this amplifier is the output is a current and input is a current. Therefore, I0 divided by II. This is a current amplifier. The gain is given by AI. AI is equal to I0 divided by II. Therefore, the current gain of this one is equal to AI. And we are taking the output current and the feedback current is given by beta times the output current. Beta times I naught is the feedback current, and the input current, which is equal to the source current, input source current IS minus the feedback current IF is the of course the input current. Therefore, this is a topology which is called current shunt feedback. As I told you already, if the sampling is current, the output impedance is increasing, as we have seen in the previous slide. Therefore, in this case also you can derive in the same method and you can get it as the impedance with feedback is given by impedance without feedback into 1 plus AI into beta. AI is the current gain of this amplifier. AI into beta. Therefore, with feedback, the output impedance is increasing if the sampling is current. If the sampling is voltage, output impedance is reducing. If the sampling is current, the output impedance is increasing. Therefore, the output impedance is based on the type of the sampling and the input impedance is based on the type of mixing. Therefore, in this case, output impedance is increasing from Z to Z into 1 plus AI into beta. That is, output impedance with feedback is given by this equation, where AI is called the current gain and beta is the feedback factor. That is, in current sampling feedback, generally in current sampling feedback circuit, the output impedance is increasing. Therefore, output impedance increasing from Z to Z into 1 plus AI into beta. Therefore, that is the observation in a current shunt feedback circuit. Now let us see the inference on different feedback networks and regarding the input impedance. As I told you, the input impedance is decided by the type of mixing. The type of mixing will decide the input impedance. Therefore, the input impedance depends upon the type of mixing, whether it is series mixing or shunt mixing. If it is series mixing, you are feeding back the voltage. If it is shunt mixing, you are feeding back the current. If it is a series mixing, the input impedance is increasing. If it is a shunt mixing, the input impedance is reducing. That is a general statement. Therefore, if it is a series mixing, the input impedance with feedback equal to input impedance without feedback. If it is a series mixing, input impedance mixing input impedance with feedback is equal to input impedance. Input impedance is if it is a series impedance is decreased. We see that if it is series mixing, the input impedance is increasing, and that is input impedance with feedback equal to input impedance without feedback ZI into 1 plus A beta. This is a generalized equation if it is a series mixing. And in that case, if it is a voltage series feedback, this A will become equal to the voltage gain AV, and if it is a current series feedback, this A will become equal to the transconductance GM, the first GM, and this A. Generally, in a series mixing circuit, the input impedance is increasing. Therefore, a type of mixing will be deciding the input impedance. Now, if the mixing is in shunt, because we are feeding back to the current, then if mixing is shunt here, the input impedance is reducing. Therefore, the input impedance decreases. That is given by ZIF equal to ZI divided by 1 plus A into beta. Therefore, in shunt mixing type, the input impedance is decreasing. And if it is there are two possibilities, the voltage shunt as well as current shunt. If it is a voltage shunt feedback circuit, this gain A will be equal to the trans resistance Rm, and if it is a current shunt feedback, this gain A will be equal to the current gain AI. Therefore, generally, if it is a shunt mixing circuit, whether it is a voltage shunt or current shunt, the input impedance is decreasing. And if it is a series mixing circuit, whether it is a voltage series or current series, the input impedance is increasing. Coming to the inference on the output impedance for the different feedback network. Now let us, output impedance is decided by the type of the sampling. If the voltage is being sampled, the output impedance is reduced. If current is being sampled, output impedance is increasing. That's a general statement. For the output impedance depends on the type of the sampling, whether it is you are sampling the voltage or current. If it is a voltage is being sampled, the output impedance is reducing. Therefore, it is output impedance with feedback is given by output impedance without feedback divided by something 1 plus A into beta, where this A can be, if it is a voltage series feedback, this A can be voltage gain AV, or if it is a voltage shunt feedback, this A can be equal to the trans resistance R. It's a trans resistance R. Therefore, generally, if it is a sampling is a voltage, it's a voltage sampling network, either voltage series or voltage shunt, both case, we are sampling the voltage from the output. In that case, the output impedance is decreasing. Then, if it is a current sampling, if you are sampling the current from the output side, generally the output impedance is increasing with Z0F equal to Z0 without feedback, that is Z0 output impedance without feedback Z0 into 1 plus A beta, where this A can be GM if it is a current series feedback, and if it is a current shunt feedback, A can be equal to the current gain AI. Therefore, generally, if the sampling is current sampling, the output impedance is decreasing. Sorry, the output impedance is increasing. Z0 equals Z0 into 1 plus AP. If it is a current sampling. And if it is a voltage sampling, the output impedance is decreasing. Therefore, the type of the sampling will be deciding the output impedance of the this feedback network, and the type of mixing will be deciding the input impedance of the feedback network.